Hi, I'm Mark Mellors, and along with Rob Berwick, we've built Tauradigm, our entry into Piwars. Previously, we've entered Piwars with Tauradigm, a fully autonomous entry, and Tauradigm builds on our learning from that. This year, we're again trying to do a fully autonomous entry. We've applied a few design principles to address issues we've previously had. In brief, they are minimization of wires and connectors, modularization, multiple sensors for redundancy and fusion, and localization. We started the design process as we usually do with a CAD model of everything. We have a very detailed CAD model of the basic chassis, all attachments, even the courses, so we can see line of sight and pinch points early on. This is the basic chassis. You see we've got the PCB is the main structural element tying together the motors and the sensors. The Pi goes on top. We have an array of time of flight sensors underneath, giving us a good view of all around. 6 motors, 6 encoders, and together they make it fast, very fast and controllable. We've put the magnetometer on this tower. Primarily that is to avoid the magnetic field from the motors. We've found in testing that they could interfere and reduce the sensitivity of the magnetometer. We use the magnetometer or electronic compass to give us our heading, so it gives us a really good insight into what direction the robot's pointing. The encoders give us a good indication of how far we've travelled, and together they give us a very good track of how far we've moved across the course. But incrementing that up produces errors, and to reduce those we're using localization, Monte Carlo localization, to take the distance sensors and combined with a map of the challenge course, we can accurately place ourselves within the course. So initially we have a model of the arena. We have a mathematical map that has the walls in it, and we fill that with an array of points, and it says each one, it could be where the robot is, and it may be 1,000 particles. And then every time we move, we go, well, the wheels moved X amount, so I'm going to move each particle that amount, assuming that all of them are our robot. And then it works out the distance from each particle to the walls in the direction they're heading, and it compares them to our actual distance values, and we weed out the unlikely particles. So the swarm that initially covered the whole arena condenses down to where the robot probably is. This is our Minesweeper attachment. It allows us to add 4 brightness sensors to the corners of the robot. They allow us to pick up which panel of the floor is lit up. So the strategy is we drive as fast as possible around the course, and when we find a lit up square we stop. A slightly strange shape is to cover the widest track possible whilst turning on the course. For Zombie Apocalypse we're using this ball launcher mechanism attachment. It uses 2 very high speed firewheels and a servo driven trigger mechanism to feed balls in extremely fast, very accurately. Has another servo attachment for adjustable aim. Our largest, heaviest and most sophisticated attachment is for the Eco Disaster Challenge. This attachment allows us to pick up barrels, determine their colour and store them into barrel storage modules. These modules can then be deployed into the appropriate areas of the course. We'll have a separate video later going into detail about the Eco Disaster attachment and our approach to the challenge.